Now in this video, we're going to go through conditional probability and independent events. Now if we were to start with conditional probability, now if we start with an event B such that the probability of B is different than 0, which means that B cannot be an impossible event. Now over here, if we have that B is realized, well, now what does it mean that B is realized? B is realized means that we already know that B has already happened. It is confirmed that B has happened. So the probability of A, knowing that B has happened or that B is realized, is called the conditional probability of A given B, and this is how it is denoted. It is denoted by A/B, which means that it's the probability of A given or on the condition that B has already happened. So this is in fact A given B. Now if we were to calculate the probability of A given B, now that would be the probability of A inter B divided by the probability of B. Now why is that? If we were to make sense of this formula, now let's just consider the sample space of a certain random experiment where we have an event A and we have another event B. Now I want to calculate the probability of A given B. So I do know that B already happened. B already happened, it means that this event is realized. And knowing that this event is realized, then we no longer look outside of that event. It is as if B becomes my total population. So to determine the probability of A, given that B is realized, since B is realized, then we look for the chance of A happening inside of B. So over here, the probability of A given B is equal to, now to find a probability, now we know that we determine the cardinal of that occurrence divided by the cardinal of my total sample space. Now over here under a conditional probability, since B has become my total population, then I divide by the cardinal of B. And to have A realized, knowing that B is already realized, so as I've already mentioned, we have to look for the chance of occurrence of A inside of B, which is the intersection of the two events. So that would be the cardinal of A inter B. So the probability of A given B is in fact the cardinal of the intersection of the two events divided by the cardinal of B, the cardinal of the set that, or the event that is realized. Now dividing both numerator and denominator by the cardinal of the sample space. So the cardinal of A inter B divided by the cardinal of omega is in fact defined by the probability of A inter B, and the cardinal of B divided by the cardinal of omega is defined by the probability of B. So to determine the probability of A given B, you could either use the probabilities of A inter B and B, or the cardinals of A inter B and B. It's in fact the same thing, they're equivalent. So it's the probability of the intersection of the two events divided by the probability of B. Now, consequences, the probability of the intersection of the two events is in fact the product of the conditional probability of A in a given B multiplying the probability of the condition, the event that is realized. Now, in fact, I can give you a quick example of a conditional probability that you are already familiar with, but you never actually knew it is referred to as a conditional probability. For example, if I give you a quick example here. Now, if I tell you that in a given population, we'd have, for example, 2/3 to be males and 1/3 to be females. Now, if I tell you that 20% of the males do swimming, for example. So if I tell you that 20% of the males do swimming, it means that I have a probability of 0.2 for the male to be swimming and 0.8 for the male not to be swimming. Now over here, this 0.2 is in fact the probability of swimming, knowing that we already have a male. So in fact, this is where you can find a conditional probability. When you take a percentage out of a percentage, now you would be referring to a conditional probability. So the 0.2 here is in fact the probability that that person swims given that he is a male, and the 0.2 here, the 0.8 here is the probability that that person does not swim given that he is a male. So whenever we say that we have 0.2 of 0.6 that swim, that 0.2 is a conditional probability. Now let's just do a very simple example here. Now if we roll a fair die once, we need to calculate the probability of obtaining 5 if we know that the outcome is greater or equal to 3. Now let's just start by defining my events. So if I define event A to be obtaining 5, and event B as the outcome is greater or equal to 3. Okay, so over here, the probability that we are looking for, we want to find the probability of obtaining 5 if we know that the outcome is greater or equal to 3. So this is my given. Okay, so over here we are looking for the probability of A given B. Now we can look at this problem from two perspectives. We can just use the formula, which is the probability of A inter B divided by the probability of B, or we can in fact look at it from a perspective of the reduced sample space. So over here, if we were to use the formula, the probability of A inter B divided by the probability of B. Now what's the probability of A inter B? Now over here, if we look at A is in fact 5. It's the singleton 5. It only has one outcome, which is 5. While B greater or equal to 3, it has 3, 4, 5, and 6. While omega, the sample space, has in fact all 6 faces as possible outcomes. So the probability of A inter B has in fact 5. Since A is a subset of B, then A inter B is A. So the probability of A inter B is 1 out of 6. So it's 1 out of 6 divided by the probability of B. B has 4 possible outcomes out of the 6 possible outcomes. So that would in fact be 4 out of 6. So canceling out the common denominator would leave me with the probability of A given B to be 1 out of 4. Now, if we were to look at this exercise from the perspective of the reduced sample space, since B is my condition, it means that B is my reduced sample space. So this is referred to as the reduced sample space. So if I want to find the probability of A given B, I need to find the chance of occurrence of A in B. Now the chance of occurrence of A in B, so we first need to look for the intersection of A and B inside B. Well, over here, 5 is in fact the outcome relative to A. So the chance of A occurring in B is 1 out of all 4. So over here, we could reach the same probability from the perspective of the reduced sample space. Now in this next example, we have 53 staff at a school where 36 of them drink tea, 18 drink coffee, and 10 drink neither tea nor coffee. Now in part A, I need to first start by determining how many staff members drink both tea and coffee. Now in order to do that, we need to first start by using a Venn diagram. So I'm going to define set T as the people that drink tea, and by C, the people that drink coffee. Now we know that we have 10 that drink neither. They don't drink coffee and they don't drink tea. So basically these 10 people are outside the two sets that are relative to T and C. Now we know that in total we have 36 that drink tea, including the intersection, so the 36 is for all tea, and we have 18 that drink coffee. So in order to determine how many staff members drink both, I'm going to define that as X, because whenever you're placing cardinals inside a Venn diagram, we start inside from the intersection and we start going outside. So if in total for T we have 36 and we have X in the intersection, then over here the people that drink tea only are in fact 36 minus X, and the number of people that drink coffee only are 18 minus X. Now our point here is to find X, but we do know that in total we have 53 staff members at the school, so the sum of all of these should be equals to 53. So we start by adding them. 36 minus X plus 18 minus X plus 10 equals to 53. Now the first two X's cancel out. We'd have 28 and 36, which is 64. So X is in fact 64 minus 53, which are 11. So we do have 11 people that drink both. So my new Venn diagram is reduced to the following. So we have T, we have C, and we have over here the school representing the total sample space. So we do have 11 here, 36 minus 11 is 25, 18 minus 11 is 7, and we do have 10 over here that don't drink tea and don't drink coffee. So this is regarding part A. Now in part B, we have two parts. We are given that one staff is chosen at random, and we need to find the probability that he drinks tea but do not drink coffee. Now, sometimes by reading the question, it gets a little bit tricky to determine if the event they're referring to is an intersection or a conditional probability. So if we look here at part I, we want the probability that the staff member chosen drinks tea but does not drink coffee. Now over here, we do not have any of the two events realized. So we're just looking for the intersections here. So we're just looking for a staff member that drinks tea and does not drink coffee. So over here, this is the probability of tea intersecting not coffee, the opposite of drinking coffee. So in this case, if we were to refer to the Venn diagram, the probability of T inter C bar is everything outside of C. So everything outside of C intersecting T is in fact 25. So this is 25 out of the total population, which is 53. So the probability of T inter C bar here is 25 out of 53. However, if we were to look at part II, we want to find the probability that he is a tea drinker that drinks coffee. Now, what does it mean that he is a tea drinker? Being a tea drinker, it means that we already know that he drinks tea. So over here, that is our condition. We already know that he drinks tea, and we want to find the probability that he also drinks coffee. So over here, drinking tea is a realized event. That is our condition. So we want to find here the probability that that staff member drinks coffee knowing that he already drinks tea. So in fact, that's the probability of C inter T divided by the probability of T. Or over here, since you have the cardinals, you could also use the cardinals instead of the probability. It's okay, it's the same thing as we've already seen, because the probabilities are, in fact, to determine the probabilities, would have to divide by the cardinal of the sample space, which cancels out in that ratio anyway. So over here, it's the intersection of C and T, which is 11, divided by the probability of T, or the cardinal of T, in fact, here. So since T is realized, then T has become my total population, which is 36. So the probability that a person that already drinks tea also drinks coffee is 11 out of 36. Okay, now in this next example, we have a deck of 52 cards, and I need to find in part I the probability that a card drawn is a red ace. So I'm going to first start by defining R to be that the event of having a red card, and by A, the event of having a card as an ace, or the card drawn as an ace. So card is an ace. Okay, so over here we have defined events R and A. So in part I want to find the probability that the card drawn is a red ace, which means that I want the card I have drawn to be red and an ace at the same time. So over here we're looking or referring to the intersection of the two events. So what we need to find here is the probability of A inter R. Now, if we were to find this probability, we'd have to look for how many cards are red and ace at the same time out of the total 52 cards. Now we know that in a deck of 52 cards we have 4 aces, out of which 2 are red. So over here, A inter R is in fact 2 out of 52, which is 1 out of 26. So we have a probability of 1 out of 26 to obtain a card that is red and ace at the same time. Now over here in part II, I'm looking for the probability that an ace drawn is red. So over here in ace drawn actually tells me that I already have an ace. So over here, my event is realized, which is having drawn an ace. That is realized. That is my condition. So over here, and I want to find the probability that that ace drawn is red. So if we were to actually find here the probability that R given A, I want to find the probability that the card is red, knowing that I have an ace. Now over here, it's the probability of R enter A divided by the probability of A. Now we could find this probability using the formula for conditional probabilities. So the probability of A enter R, we already found it here, which is 1 out of 26. And the probability of A, what's the probability of drawing an ace? It's in fact 4 out of 52. And we already know that this is the same as 2 out of 52, which is 2 out of 4, which is half. Now we could have obtained this probability by in fact looking at the problem from the perspective of the reduced sample space. Now since I know that A is realized, now I have 4 aces. 4 aces in my deck of 52 cards. So these 4 aces become my total population or my reduced sample space. So out of these 4 aces, I have 2 that are red and 2 that are black. So if I know that I have an ace, then the probability of having a red card would be 2 out of 4. So the probability of R given A is 2 out of 4, which is half. And we go back to the same probability that the formula has already given us. Now, if we were to define what independent events are, now A and B are independent events if realizing event A does not affect realizing event B or vice versa. Realizing event B does not affect realizing event A. So in fact, we would look at 2 events to be independent if the probability of A given B would be equals to the probability of A. So by realizing B, the probability of A does not change. So which means that A and B are independent. So whether I already have B realized or not, the probability of A does not change. So the probability of A given B is equal to P of A, and similarly the probability of B given A would be equals to the probability of B, since A and B are independent from one another. So realizing event A would not affect realizing event B. So as a consequence, the probability of A enter B would be equals to the probability of A times the probability of B. Now, the probability of an intersection is not always the product of the probabilities of the 2 events. If A and B depend on each other, the probability of the intersection would not really be the product of the probability of the 2 events. Now, why is it that if A enter B, if A and B are independent, then the probability of A enter B would be equals to the probability of A times the probability of B? Now, that would be because of the conditional probability being equal to the probability of the original event. So the probability of A given B, we know that it's the probability of A inter B divided by the probability of B. Now, if A and B are independent, we have seen that this probability of A is equal to the probability of A. So we would have the probability of A equals to the probability of the intersection divided by the probability of B. Now, if we cross multiply, we end up with this corollary, or with this consequence. Okay, now before we move forward to the examples, it's really important not to confuse between two events that are mutually exclusive or disjoint and with two events that are independent, because this is where most people get confused. It's the difference between mutually exclusive or independent event. Now, I'd remind you that mutually exclusive events are two events that cannot happen at the same time, which means that the probability of their intersection is 0. While independent events are events that do not affect each other. It means realizing one does not affect realizing the other one. So it's very important not to confuse independent event with mutually exclusive event or disjoint events. Okay, so in this example, we have an urn that contains 10 marbles in total, out of which 4 are red and 6 are black. And we draw 2 marbles successively and with replacement. So over here, we're not drawing the marbles simultaneously, we're drawing them successively as one after the other one. And it's with replacement, which means that when I draw the first one, I note its color and I put it back in the urn. So I consider the events A, the first marble is black, and B, the second marble is red. Now, why is it that these two events are independent? It's because the experiment is done with replacement. So the choice of the second ball or the second marble is not affected by the choice of the first one, because the first one had its color noted and put back in the urn. So the choice of the second one was not affected by the choice of the first one, because following the first marble, the urn did not change because I put back that marble back in the urn. So in this case, A and B are independent events. So the probability of A inter B would actually be the probability of A times the probability of B, and the probability of A would actually be it's the first one being black, so it's 6 out of the 10 I already have in the urn, and the probability of B is 4 out of 10 because I have 4 red marbles out of 10. However, if this experiment were to be done without replacement, which means that when I draw the first ball, I note its color and do not put it back in the urn, I just put it aside. In that case, events A and B would not be independent, because in that case, the choice of the second marble would depend on the choice of the first one, because, for example, if the first one was a red, the total number of marbles in the urn would actually become 9 instead of remaining 10, and the number of red or black marbles would actually change inside the urn. So the choice of the second one would then depend on the choice of the first one. Now in this example, we have Micah that goes on a safari. The probability that she takes a photo of a cheetah on any day is 0.3. So if the safari lasts 10 days, find the probability that Micah takes at least one photo of a cheetah. So over here, if we were to look at the probability that she takes a photo of the cheetah on any day, it's 0.3. So during these 10 days, every single day, the probability that she takes a photo of a cheetah is 0.3. So the probability of taking the photo of a cheetah on any day is independent from the probability of taking a photo of a cheetah on any other day. So taking a photo on day 1 is independent from taking a photo on day 2, which is independent from taking a photo on day 3, etc., all the way to the 10th day. So over here, however, if we look at the probability they're asking for the probability that Micah takes at least one photo of a cheetah, and that is during all 10 days. So over here, if I were to call the event A, that Micah takes at least one photo of a cheetah during these 10 days. Now, since we want the probability of having at least one photo, at least one, so over here it's easier to find the probability of the opposite event, which is Micah doesn't take a photo of a cheetah during 10 days. So over here, in fact, if the probability on every day, if the probability of taking a photo of a cheetah is 0.3, then the probability of not taking the photo of a cheetah on one day is 0.7. So during 10 days, since taking a photo on one day is independent from taking a photo on another day, it means that not taking a photo on one day is also independent from not taking a photo on any other day, which means that the probability of A bar not taking a photo during 10 days, if every day of these 10 days we have a probability of 0.7 of not taking a photo, then the probability of not taking a photo during the 10 days is 0.7 multiplied by itself 10 times, because the probability on each day is 0.7, and not taking a photo on one day is independent from not taking a photo on any other day. So the probability of their intersection is in fact the product of these probabilities. So over here, the probability of A bar is 0.7 to the 10. So the probability of A bar being the opposite event of A, so that would be 1 minus probability of A bar, which is 1 minus 0.7 to the 10. Now, whatever that is equal to, we could use our calculators in order to determine that probability.